Hello, my name is Ioana Diala. This talk is about transparency dictionaries with succinct proofs of correct operation. This is joint work with Abhiram Kothaparli, Brian Parno, and Srinath Sethi. A transparency dictionary is an untrusted service that maintains a mapping from labels to values. Users can update the entries in the dictionary and look up the values associated with labels. Transparency dictionaries have been proposed as a foundation for several applications, such as public key infrastructure and end-to-end encryption. In the context of end-to-end encryption, the dictionary maps each user ID to the user's public keys. When the service is working correctly, it enables two users, Alice and Bob, to communicate securely. If Alice wants to receive encrypted messages, all they need to do is generate a key pair and register their public key to the dictionary. When Bob wants to send an encrypted message to Alice, they query the service for Alice's public key. Then they use Alice's public key to encrypt the message and send the encrypted message to Alice. Because Alice is the only one that knows the corresponding secret key, she is the only one that can decrypt and read the message that Bob sends. Observe that the secure communication between Bob and Alice relies on the dictionary service operating correctly. If the dictionary is controlled by a malicious actor, they could send to Bob their own public key for which they know the matching secret key. Then they could do a man-in-the-middle attack to read all messages that Bob sends to Alice. First, they would decrypt all messages that Bob sends with their secret key, and then encrypt them again using Alice's public key and send them to Alice. Alice and Bob cannot be sure that no one is eavesdropping unless they have some assurance that the service is operating correctly. Ideally, this assurance will come from the transparency dictionary itself. Whenever the dictionary executes some operation, it will produce a proof that attests that this operation was executed correctly and send this proof to the users. When we say that the service is executing correctly, we mean that there are some rules that the dictionary is supposed to obey while executing, and the proofs should demonstrate that these rules are not violated. First, whenever the dictionary replies to a lookup query, the value that is returned should correspond to the value associated with the requested label. Second, the dictionary cannot arbitrarily erase labels. This implies that the set of labels in the dictionary should grow monotonically. Third, the values associated with the label should only be updated according to an application-specific policy. For instance, in the case where the dictionary is used for end-to-end encryption, it might be required that any updates to a user's set of keys are authorized by the user. This can be enforced by requiring that all new keys are signed by one of the user's keys that is already in the dictionary. Additionally, we require that the proofs produced by the dictionary have some useful security properties and that they are efficient. Specifically, we want the proofs that the service creates to be publicly verifiable, meaning that any client in the system should be able to verify these proofs independently and gain assurance that the service is well behaved. Second, we would like for the proof generation and verification process not to require any trusted setup or rely on any trapdoors. Third, we require that verifying proofs is fast. By fast, we mean that verification should be less expensive than re-executing the operations of the service. This implies that the proofs should be succinct. Last, we require that the overheads of generating these proofs are modest. This means that generating these proofs should be affordable for the dictionary. In many applications, such as the end-to-end encryption one, the clients cannot wait hours or days for their updates to the dictionary to go through, especially if they want to revoke a key whose security has been compromised. Prior work fails to meet all these requirements. A large body of work fails to meet the first three requirements. Konix and Merkle Square provide untrusted setup and efficient verifiability, but do not provide public verifiability, and on top of that, they incur high storage overheads both asymptotically and concretely. AAD provides both public verifiability and efficient verifiability, but requires a trusted setup and additionally imposes high proving overheads at the service. Keybase, Seamless, Concerto, and Fastware provide public verifiability and don't require a trusted setup. However, they fail to meet the efficient verifiability requirement, and in these systems, verification is proportional to the number of updates. There is a lot more work in this area. You can check our paper for a detailed comparison with other systems. None of them satisfies all three requirements. There is one exception. These are the works that combine zero-knowledge proofs, or otherwise ZK SNARKs, with cryptographic accumulators. These works provide both public verifiability, untrusted setup, and efficient verifiability. However, they incur high proving overheads. This is the approach that we take in this work. We built Verdict, a transparency dictionary that satisfies all the above requirements and admits modest proving overheads. Verdict works in epochs. At the beginning of each epoch I, the service commits to its state by publishing a digest DI to a public timeline. This public timeline can be a public ledger, such as a blockchain. It also publishes an update proof PI, on which I will elaborate in a bit. During the epoch, the service receives requests from users to register new labels and update the values of existing labels. The service buffers all these update requests, and at the beginning of the next epoch, it applies them to the dictionary. Then, it computes the new digest DI+1 of the new state and publishes it at the public timeline. It also produces a SNARK proof PI+1 that attests that the transition from the state that corresponds to the digest DI to the states that correspond to the new digest DI+1 was correct. That is, the proof is valid only if all the updates that the service applied did not delete any existing labels and updated the values of labels according to the application-specific policy. Users validate all update proofs that the service publishes in the public timeline to make sure that the service executes updates correctly. When user Bob lookups Alice's key, the service sends back the answer along with a lookup proof that demonstrates that the answer is consistent with the latest public digest. If Bob has verified all proofs in the public timeline and the verification of the lookup proof checks out, then Bob is sure that the answer indeed corresponds to the key that Alice has registered. Verdict's practicality relies on all the above proofs to be succinct and quick to generate. We achieve this by building a new ZK SNARK that the service uses to generate proofs without incurring high overheads. Also, we design a new SNARK-friendly cryptographic accumulator through which the service represents its state. Both of these contributions are of independent interest, and I will present them briefly. We designed a new ZK SNARK that meets Verdict's requirements. We call this new ZK SNARK Phalanx. Phalanx does not require a trusted setup, and its security relies on the symmetric external Diffie-Hellman assumption. Also, in the paper, we present another version of Phalanx, whose security relies on the discrete log assumption. Phalanx produces amortized constant-sized proofs with constant verification times. This implies that the size of the update proof that each user needs to download at each epoch is constant. And the same is true for the work that each user needs to do to verify the epoch's update proof. Users are also required to download and verify a logarithmic size proof whenever they issue a lookup query. We designed Phalanx to leverage the SIMD patterns at Verdict's workloads. As a result, in the context of Verdict, generating proofs with Phalanx is more than 10 times faster than with Spartan, the system which has the prior fastest ZK SNARK prover. We also design a new SNARK-friendly cryptographic accumulator. What SNARK-friendly means is that the insert and update operations of this accumulator can be efficiently represented in the circuit that our SNARK uses. The key to the efficiency of this accumulator is that both its memberships and non-membership proofs can be efficiently encoded in a circuit. Our accumulator is a variant of textbook Merkle trees. Textbook Merkle trees support SNARK-friendly membership proofs, but they do not provide non-membership proofs. On the other hand, there exists a variant of Merkle trees that are called sparse Merkle trees. These support both membership and non-membership proofs. However, their non-membership proofs are not SNARK-friendly. Our accumulator provides SNARK-friendly membership and non-membership proofs by encoding metadata inside leaf nodes. We implement Verdict as a generic library for producing proofs of dictionary operations. Our implementation comprises approximately 10,000 lines of Rust code. To evaluate our system, we use 3 baselines. First, the system of append-only authenticated dictionaries, or AAD. Second, a naive baseline based on Merkle-Patricia trees. Third, an optimized version of the naive baseline based on Merkle-Patricia trees that batches proofs. We call this naive baseline naive++. We evaluate the 3 baselines with respect to their proofs, the lookup proofs and the update proofs. For the lookup proofs, we compare the proof size and verification time under all systems. As for proof generation times, it is memory bound on all systems, and all systems perform similarly on this metric. For update proofs, we compare the systems on proof generation time, proof size, and verification time. Lookup proof sizes and verification times depend on the size of the dictionary under all systems. The naive and naive++ baselines handle lookup proofs identically, so we only present naive in the graphs. Verdict has the smallest lookup proofs among all baselines. As for verification time, verifying lookup proofs under Verdict takes at most 5 milliseconds. This is more efficient than verifying them under AADs, but more expensive than verifying them with the naive baselines. The performance of all baselines on update proofs depends on the number of updates per epoch and the size of the dictionary. I will only talk about our performance as a function of the dictionary size, but please see our paper for more experimental results. Verdict has the smallest proof sizes among all systems. They are constant sized and amount to 651 bytes. The verifier is also constant and runs in 4 milliseconds. It is faster than all systems for dictionaries with more than 65,000 labels. Generating update proofs under Verdict takes around 70 seconds. This is at least 4 orders of magnitude more efficient than AADs, but more than 4 orders of magnitude higher than the naive baselines. And this is the main limitation of Verdict, namely that producing SNARK proofs of updates still requires substantial CPU. We could possibly mitigate these costs in the future by using GPU or ASIC acceleration. To summarize, Verdict represents a new point in the design space for transparency dictionaries. It enables all users to verify that it is operating correctly. It does not require a trusted setup. It produces succinct proofs, and the overheads that it imposes to the service are affordable. Verdict's efficiency relies on 2 techniques that may be of independent interest. First, a ZK SNARK optimized for epoch-based services that provides amortized constant-sized proofs and does not require a trusted setup. Second, a new SNARK-friendly cryptographic accumulator that provides efficient non-membership proofs.